Recording in progress.
All right, hello and welcome back to Math 3321, Math Concepts 1. We're going to be looking at section 1.2 today in our book. So these slides are posted on Canvas, but here's a video of me talking through them. All right, so section 1.2 is all about explorations with patterns. You should be able to understand and explain finding patterns and determining if a pattern holds, using deductive and inductive reasoning and when to use them. And I will tell you what those things mean. And identifying different types of sequences, arithmetic, geometric, and Fibonacci sequences. And then you should be able to find the nth term of certain sequences. So given a pattern, what's going to happen, some vague place in the future. And determining differences to find a pattern for neither arithmetic nor geometric sequences. All right, so if we want to look at these different equations that we have here, take a second, pause the video, try to find some things that you identify as patterns. All right, so you may have noticed a few different things in these equations. So, for example, the numbers on the far left, right here, these are all natural numbers, and they are starting with a 1 and getting 1 greater every time. So 1, 2, 3, 4, 5 are the numbers that we're starting with in our sum of the left-hand side of the equation. So something else you could have noticed is that these numbers here in the middle, these are all products. So we're multiplying two numbers together. The second number is always 9. So that's a pattern. What do you notice about the first numbers that we're multiplying together? So we start with 0, and then each of the subsequent parts of our product are the numbers that are generated by putting together the first few digits. So 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Now you may also notice that we have a pattern here on the sum on the right-hand side of our equation. We have 1, 1, 1, then we have 3 ones, 4 ones, 5 ones. So you might be asking yourself, I hope, does this keep going? We could try it with the next part of the pattern would be 6 plus 1, 2, 3, 4, 5 times 9. What is that? We can put it into our calculators and figure it out. So if I say 6 times, excuse me, well, I should do 1, 2, 3, 4, 5 times 9 first, plus 6 is in fact 1, 1, 1, 1, 1, 1. So this will keep going for at least the next equation. But does it keep going forever? That's a question we could ask. So do the patterns continue? Why or why not? The pattern appears to continue for a number of cases, including the one I just showed you, but it actually doesn't continue in general. So if we look at this example, what we might call a counter example to the pattern continuing forever, we have 13 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. So this is 10, 11, 12, right? So those are our next numbers in line, times 9. Then we get 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 9, 1, 0, 0, 2, 1. So this doesn't work anymore because we don't have the same pattern where we have all ones on the right-hand side. So this actually is going to stop working. The pattern's going to break when the pattern of digits being multiplied by 9, so this number here, when we start to have repeated digits. So when we get this 1 here, the pattern's going to stop happening for us. So inductive reasoning is something that we do when we make generalizations based on observations and patterns. So these are things that lead us to conjectures or guesses, statements that we might think are true, but we haven't proved. And we can prove statements or conjectures false by using a counterexample like we just did with this 13 example. Now, inductive reasoning can be used with patterns and numbers, or it can be used in patterns in our everyday life, right? Like I took a course with Dr. Heath last semester, the semester before that, and the semester before that, and I made an A in all three. So I'm going to make an A in this semester, right? That's a pattern. Now, if you don't do the work, then you might not get an A in Dr. Heath's class this semester. So that would be a counterexample if you got a bad grade in a class that you took with the same professor, right? So these are things that we think might be true based on a pattern, but we haven't proved, and we can prove them false with a counterexample. So there are dangers of making conjectures. So here's an example where we might run into some problems with just assuming that a conjecture that we make is true. So in this example, you can choose points on a circle and connect them to form distinct non-overlapping regions. In this figure, 2 points determine 2 regions. So if we look at this picture here, we have a circle with this circle with 2 points on it, and then we have one region here and one region here, right? So we have 2 points making 2 different regions. 3 points, when we put 3 different points on the circle, we're going to get 1, 2, 3, 4 regions of the circle. When we do the same thing with 4 points on the circle, we're going to have 1, 2, 3, 4, 5, 6, 7, 8 different regions that are not overlapping. So we might ask ourselves, what's the maximum number of regions that we could determine by 10 points? So we might start approaching this problem by first thinking about 5. Now we saw a pattern here, right? That the number of regions is actually doubling every time we add another point and connect it to the others. So it might lead us to guess that when we have 5 points, we have twice as many as we did with 4 points. So that would be 2 times 8, because 8 was what we had with 4 points. So it would be 16, which is 2 to the 4th. So 2 to the 4th is what happens when we take the other number, multiply it by 2, the previous number of regions, and multiply it by 2. So we could first, we might think that if our conjecture is right, that it's going to double every time, then we would have 2 to the 9th if we have 10 different points, right? Because we're going to take if we make a table and this is the number of points, and this is the regions, then with 2 points, we had 2 regions. With 4 points, we had 4 regions. Oh, excuse me. With 3 points, we had 4 regions. With 4 points, we had 8 regions. With 5 points, we're guessing that we'll have 16 regions. So this is 2 to the 0 power, 2 squared, 2 to the 3rd power, 2 to the 4th power. Keep on going. We might assume that with 10 points, we would have 2 to the 9th, or 512 different regions. So an initial check for this conjecture would be to see if our very next step works. So for 5 points. All right, so if I draw a circle and add 5 points to it, my job is to figure out how many different regions I will have. So I connect all of them. think I've connected them all. Then I can count them. So my guess is 16 based on our conjecture. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So it looks like it worked for 5 points. Here's the textbook's version of counting this. So for 6 points, the pattern predicts that the number of regions will be 32. So if we try to do it again with 6 points, one, two, 3, 4, 5, 6. And then I'm going to connect them all. Oh, I messed up my points. Okay. You have to be careful not to make regions that don't actually exist. All right, so if you trust me that I have drawn all the regions, then we can start counting, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, wait, I'm missing a line. I'm missing this one. That's okay. You can keep counting. 12. 13 is the one I missed here. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so I'm too short. So there are actually 31 regions. Well, I missed counting one. Here's your challenge problem. Figure out which one I didn't count because I missed one. But there are actually 30 regions and here 31 regions, and here's their drawing of it. And so the pattern stops working here with 6 points. So we can say that our pattern is probably not going to work for 10. All right, so moving forward, we have sequences. Sequences are an ordered arrangement of numbers, figures, or objects, and they can be classified based on their properties. So an arithmetic sequence is a sequence in which each successive term is obtained from the previous term by addition or subtraction of a fixed number, or the difference. So we might ask ourselves, is 2, 5, 8, 11, 14 an arithmetic sequence? So we can figure this out by asking ourselves, well, what's the difference between each of them? Are we adding the same number every time? So to get from 2 to 5, we would add 3. To get from 5 from 8, we also add 3. To get from 8 to 11, yeah, we add 3. 11 to 14, we add 3. Yes. So this sequence is an arithmetic sequence because the difference between each term is 3. So we could look at an example that's not using numbers, but rather matchsticks, or the pattern is in the number of matchsticks needed to continue the pattern. So we would ask ourselves, okay, how many matchsticks did we need here? 4 to make the square. And then to make the next one, we could just count. We could say 1, 2, 3, 4, 5, 6, 7. 7 needed here. Or we could start to make an observation, right? That this is the previous pattern. and I'm adding 1, 2, 3 matchsticks every time. So this is 10. I'm going to have to add 3 more to that, 13. So I don't have to count every time. So this is also an arithmetic sequence because we're adding 3 matchsticks each time. So the pattern is 4, 7, 10, 13, 16, 19. All right, so if we have a pattern that is, or yes, a sequence that's determined by AN, so the term number N is 4 times N plus 3, we want to know if it's going to be arithmetic or not. So one way we might do this is with a table. So N is the number of term in the sequence, right? So this would be A1 equals is the when N is 1, A2 is when N is 2, A3 is when N is 3, A4 is when N is 4, etc. And then AN is given by 4 times N plus 3. So 4 times 1 plus 3 is 4 plus 3 is 7. 4 times 2 plus 3 is 8 plus 3, 11. 4 times 3 plus 3 is 12 plus 3, 15. And 4 times 4 plus 3 is 16 plus 3 is 19. So the question is this sequence seeming to be arithmetic or not? So is there a same difference between each of these terms? So if there were, what's the difference between 7 and 11? We would have to add 4 to get from 7 to 11. To get from 11 to 15, we also would have to add 4. To get to 15 from 19, we have to add 4. So it's looking like this would be an arithmetic sequence. And then here's the same work. All right, so here's another one. We want to find the first 4 terms of a sequence that's given by n squared minus 1. So when n is 1, 2, 3, 4, we're looking for n squared minus 1. So A1 will be 1 squared minus 1, which is 1 minus 1 or 0. A2 is 2 squared minus 1. 4 minus 1 is 3. A3 is 3 squared minus 1. 9 minus 1 is 8. And A4 will be 4 squared minus 1. So 16 minus 1 is 15. So is this an arithmetic sequence? Are we adding the same number to get from one term to the next every time? So 0 plus 3, or 0 plus 3 is 3. 3 plus 5 is 8. So we're not adding the same number every time. 8 plus 5 is actually 7. So no, this is not going to be an arithmetic sequence. But you do see there is actually a pattern here, and we'll get to that a little bit later. We're adding 2 more every time. So that's interesting. So it's not arithmetic because it has no common difference. Okay, so here's a practical example we could use with sequences. So say we have a theater set up in a way that there are 20 seats in the first row and 4 additional seats in each consecutive row. And we know that the last row has 144 seats. How many rows are there in the theater? So A1, or the first row, or first term in our sequence, is 20. AN, or the nth row, which is the last row, has 144 seats. And D is 4, the difference. D is for difference in this equation here. So AN is determined by the very first row's number of seats plus so many more rows adding D. So if I draw this out, right, then we start with 20 seats here. The second row is going to have 20 and 4 more. The third row is going to have 20, 4, because we're adding 4 onto the last one, and 4 more. So n minus 1 up till we get to n, the nth row, we're going to have 20, which is a1, plus so many sets of 4 numbers. So 4, 4, however many times it takes to get 4. And this is going to be added n minus 1 times. All right. So this gives us that, 144 seats is given by the original number of seats plus n minus 1 additions of 4. So we can solve this algebraically by subtracting 20 from both sides and then dividing by 4 on both sides, finally adding 1 to both sides. So there are 32 rows in the theater. All right, and then moving on from arithmetic sequences, we have a different sequence called the Fibonacci sequence. The Fibonacci sequence is actually pretty fun. We don't get into it too deep in this class, but if you have any interest in it, I'd love to talk to you about it more. But it's defined by the nth term is equal to the sum of the 2 terms before it. So for n equals starting 3, 4, 5, the Fibonacci sequence only works when we start where n is equal to 3, right? Because we can't subtract n minus 2 would not make sense if we started with n equals 1. We can't have a -1 term. So the sequence starts with 1 and 1. And so given the way this is defined, the third Fibonacci number, F3, is F2 plus F1. F2 is 1, F1 is 1. So F3 is equal to 2. And so we get the third Fibonacci number by adding together 2 and 1. So 1 plus 2 is 3. Then 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And it keeps going that way. So this is a Fibonacci sequence. And then the last type of sequence we're going to talk about formally in this lesson is a geometric sequence. So this is where instead of adding the same number every time, we're going to multiply the same number every time to the previous term. So this is called the ratio. So in an arithmetic sequence, the number we add every time is called the difference. In a geometric sequence, the number we multiply each term by, or the previous term by, is called the ratio. So we could ask ourselves, is 2, 6, 18, 54, 162 a geometric sequence? So what would we need to multiply 2 by to get to 6? 3. 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. So it does seem like this is a geometric sequence with a ratio of 3. Because if we multiply each term by 3, we get the following sequence entry. And then just to clarify, we've been talking a little bit about powers throughout the lesson, but to formally define it, the power a to the n is defined to be multiplying a by itself in different times. So if n is equal to 0, and a is not 0, then we have a convention in mathematics that a to the 0 power is 1. And then we have other sequences. There are figurate numbers. So the triangular numbers are formed by the number of dots that it would make to make that shape. So 1, 3, 6, 10 is the triangular numbers. And then we have the square numbers too. And then finally, we might come across sequences that don't have an arithmetic or geometric pattern explicitly. So if we ask ourselves here, all right, so could this be an arithmetic sequence? 5, 6, 14, 29, 51. We're not adding the same number every time because here the difference would be 1. The difference between 6 and 14 is 8. The difference between 4 and 29 is 15. The difference between 29 and 51 is 22. And the difference between 51 and 80 is 29. And you can use your calculator to do any of these calculations. But it's clear that this is not an arithmetic sequence because we're not adding the same number every time. We could also ask ourselves, is this a geometric sequence? Are we going to be dividing or multiplying by the same number every time? And that doesn't seem to be the case either, right? These are actually pretty ugly numbers when you think about their ratios, 5 and 6, 6 and 14. But the ratio of 5 and 6 is not the same as the ratio of 6 and 14. So this isn't a geometric sequence either. But one strategy you could try, if you're given a pattern that you can't seem to identify as arithmetic or geometric, is to look at the patterns of the patterns. So if we look at this sequence here, 1, 8, 15, 22, 29, what you'll actually see is that this is an arithmetic sequence. 1 plus 7 is 8. 8 plus 7 is 15. 15 plus 7 is 22. And 22 plus 7 is 29. So the terms in the given sequence are adding by an arithmetic sequence. So they are not arithmetic, but their differences are arithmetic. So if we add 7 to 29, we should get 36. And so 36 is what we should add to 80 to get our next term. So 80 plus 36 should be 116. So here's just this worked out in the PowerPoint slide as well. And that's the end of this lesson. So again, thank you for watching. Always email me if you have questions. You should be prepared to do your section 1.2 homework on MyLab Math now. And I am here as always if you need me. Thank you.